So in this short podcast, we're just going to look at several of the gas laws and just kind of how they came about, their relationships. A lot of this is going to be reviewed from general chemistry or honors chem, but the first relationship is PV equals PV. Typically we don't see it like this, but we see P1V1 equals P2V2, and this is known as Boyle's law. For the most part for AP, you don't need to know the laws that are associated with the formulas, but know their relationships. So if a product equals some constant, because really P1V1 equals some value, let's call it N, or N is probably a bad value because N is moles and we're talking about gases, so let's call it X. So if P1V1 equals X and P2V2 equals X, then P1V1 must equal P2V2. So if we change pressure, how does that affect volume, and vice versa? And this relationship is known as an inverse relationship, because as one of our variables gets larger, the other one must get smaller to maintain the constant that they are, their product is equal to. All right. Another one is this: P over T equals P over T. And again, in general chem, this would have been P1 over T1 equals P2 over T2. And from this, we have a quotient, and our quotient equals some constant x. So if our denominator gets smaller, our numerator has to get smaller, and opposite of that. So this is a direct relationship, and this happens to be Guy-Lussac's law. And then another one you're probably familiar with is V1 over T1 equals V2 over T2, and this is known as Charles' law. And again, this is a direct relationship. And the other one that's a little bit less common is V over N. So V1 over N1 equals V2 over N2. And this is known as Avogadro's law, which just says the more moles you put in, the greater volume something's going to take up. So again, this is a direct relationship as well. So these four laws, and again, you don't need to know their names, really led to this conclusion, that if we isolate a gas, pressure times volume divided by N times T, or moles times temperature, equals some constant. Okay? If we change this, so we could have P1V1 N1 T1 equals P2V2 N2 T2, but again, they equal some constant. And they found that this constant was constant for a specific gas. So not all gases are the same, but P1V1 Nt is going to be the same for hydrogen, and then we change one of those variables, everything's going to change accordingly. All right. So this really became known as R. All right. And this led to the ideal gas law, which is PV equals nRT. Sometimes here as PivNert. All right, where pressure is P is pressure, V is volume, N is moles, T is temperature, and R is the ideal gas constant. All right, and this is where we want to focus right now. So typically, this has a value of 0.0821. All right, and the units on this are very important because this number goes with the units. And this particular value has units of liters times atmospheres over moles times Kelvin. All right, and why is that? Well, that comes right from this equation. Because what is volume measured in? Liters, pressure is measured in atmospheres, N is measured in moles, and T is measured in Kelvin. All right, so this is assuming our pressure is 1 atmosphere, and the molar volume of a gas at STP, again, STP means standard temperature and pressure, it is 22.4 liters. So standard pressure is 1 atmosphere. N is how much a mole takes up, so that's 1 mole. And then standard temperature for gases is 273 Kelvin. So simply if we take 1 times 22.4 divided by 1 times 273, we get this numeric value. All right? So this is not metric. All right? This is one of those few constants that we use quite a bit in science that's actually not the metric constant. So this podcast is, I want to go over what is the metric constant. Okay? So the issue becomes this pressure right here. So atmospheres is not the metric way to measure pressure. All right? So the metric way to measure pressure is the kilopascal. In kilopascals, their standard value is 101.3 kilopascals is standard pressure, and that equals 1 atmosphere. Alright, so what we're going to do is we're really going to substitute these values in and see what we get. So we're going to have 101.3 kilopascals times 22.4 liters. And all that's going to be divided by 1 mole times 273 Kelvin. And we do this math, we get 8.31. Alright? And the units for this seem like they're going to be kilopascals times liters all over moles times Kelvin. But rarely do you see this as the unit. Alright, so again, this is what we want to go over. So there's really two values for R. The ideal gas law, which you saw in general chemistry, and then this one, and I want to show you the equation at the end, we're going to use this value. Alright, so real quick, I'm just going to scroll down. Alright, so bear with me here, but we're going to find out where this unit comes from. So real quick, in chemistry, we have several values. Pressure is equal to force over area. If you've taken physics before, maybe you're in physics, force is equal to mass times acceleration, again, over area. So we're going to put some units on this now. So our SI unit for mass is the kilogram. And our area is length times width, so that's going to be meters squared. I'm sorry, that's acceleration, not area. Area is on the bottom, so I'll do that real quick. Meters squared. And then acceleration is meters per second squared. Alright, so we have something kind of like that. So that's really our unit for pressure. Kilograms meters over meters squared second squared. Typically we're not going to do it like that because our meters cancel, so we really have kilograms over meters second squared. Alright, so that is pressure. And what we do, we multiply that by our volume. Okay, so real quick, a liter is the same as a cubic decimeter. Okay, and a decimeter is 0.1 meters. All right, so a liter is equal to 0.1 meters cubed, or we can say a liter is equal to 0.001 meters cubed, because this 0.1 is cubed along with our meter. All right. So hopefully you're following there. So I have my next unit that I'm going to throw in is going to be meters cubed. Alright? So right now I have pressure times volume all over moles times Kelvin. Okay, so we're going to throw in some numbers now. So we're going to use 101.3 kilopascals. We're going to multiply that by, notice now, 0.0224 meters cubed. Is that right? 22.4? That's right. All right. All over 1 mole times 273 Kelvin. Okay? So what happens is this kilo really makes this number 1,000 times bigger. Okay? But really, we just want to move this decimal 3 times. Alright? So this kilo, we're going to get rid of the kilo and really multiply this by 1,000. It's all multiplication, so the order of operation doesn't matter. Alright, so I'm going to get from here still 8.31. Alright, so 8.31. And then what we have left is, again, a pascal is a kilogram meter second squared. And what we end up having is a kilogram meters squared second squared all over moles Kelvin. And again, if you've been in physics before, you know that energy is 1/2 mv squared, or kinetic energy. So m is mass, and then v squared is velocity squared, so meters over second squared, which is that. So anyways, this is known as a joule. So really, when we use 8.31 as our constant, the unit we usually use is joules per mole Kelvin. All right, instead of kilograms, liters, moles, Kelvin. So that is all I wanted to set up, is how we derive the 2 units for R. 0.0821 is the one you've seen before, but 8.31 is useful in this instance. All right, so we have this equation, which is known as the root mean square velocity. Sometimes it's an R for rate, sometimes it's a V, but you have this little RMS for root mean square. And the way we solve this is the square root of 3RT over molar mass. Alright? So when we use this equation, because we want a speed at the end, we want to isolate this meter squared second squared, is really what we want to do. So if we just look at units, we want the square root of 3 times kilograms meter squared second squared, and then T is going to be Kelvin. But what's the denominator of our R? Well, it's all over moles times Kelvin. And then we're going to place that over molar mass. And this is the only time in chemistry that molar mass is this. Usually molar mass is grams per mole. So we're going to have something over mole. Alright, so bear with me, and just watch this. Kelvin is going to cancel out. Moles is going to cancel out. We want meters squared over second squared, so if we take the square root of that, we get meters per second, which is what we want for velocity. So this is the unit we want to end with. So because of all that, what has to be my unit for my molar mass? It has to be kilograms per mole. Alright, so if I get kilograms per mole, I'm left with meters per second. Meters squared over second squared, square root of that is meters per second. So, a couple things with this equation. R is the 8.31 R, and molar mass is in kilograms per mole. Right? And what that's going to do is, at a given temperature, it'll tell you what the root mean square, or the average speed of molecules are of a specific mass at a given temperature. Because molar mass is in the denominator, we're going to find that the smaller our mass, the faster our gas moves at a given temperature. So hydrogen gas, because it only has a molar mass of 2, or 0.002 kilograms per mole, or 2 grams per mole, is our fastest gas at a given temperature. Or something like sulfur dioxide, which has a molar mass of 64 grams, or 0.064 kilograms per mole, is going to have a much slower average speed at a given temperature. So anyways, that's just a real quick summary of kind of gas laws, from Boyle's law down to the ideal gas law, and then down to calculating a root mean square, and how you derive the 2 R values that are pretty common in chemistry.